This is a follow-up to my video on fully auditable voting systems. Please watch that video first. A viewer privately asked how to compute how many people need to check their confirmation codes or to spoil ballots in order to verify with high confidence that the election outcome has not been corrupted. Here is my response. Consider the following scenario. In the election, Edward and Jacob actually received K votes each, a perfect tie. The election authority is Team Edward, so it steals B votes from Jacob and gives them to Edward. Technically, the election authority could swing the election by stealing a single vote, but it's probably going to try to make the results look plausible, plus it needs to leave some breathing room for things like provisional ballots. The published tally is then Edward K plus B votes and Jacob K minus B votes. The published margin of victory is 2 times B votes. Expressed as a fraction, the published margin of victory, which we're calling MOV here, is 2b divided by 2k, which is equal to b divided by k. We'll make the following assumptions. First, the election authority wouldn't bother trying to cheat if it has at least a 90% chance of getting caught. It turns out not to matter very much whether you assume the number is 90% or 99%, so long as there is some probability of getting caught that you consider high enough to deter the election authority from cheating. Next, when a Jacob voter checks her confirmation code or spoils a ballot, she is effectively trying to draw a black ball out of a bag containing K minus B white balls and B black balls. The white balls represent the votes that were not cheated. The black balls represent votes that were cheated. Third, if any voter draws a black ball, then the election authority is proven to have cheated, because remember, if the election authority is caught cheating, there is definitive proof of that. To make things easier, we'll neglect the fact that every time a white ball is drawn, it slightly increases the chances of drawing a black ball later. So the number of voters who need to check is actually slightly lower than what we'll compute here. I could go through a mathematical derivation at this point, but most viewers who would understand that are also capable of doing that derivation for themselves. So instead, let's do the thing of the moment and ask ChatGPT. So the question is, if I have a bag containing K minus B white balls and B black balls, then how many balls do I need to draw with replacement in order to be 90% certain of drawing at least one black ball? The answer is approximately natural log of 1/10 divided by natural log of 1 minus b divided by k. This is the correct answer. Incidentally, I ran this query several times, and some of the answers were incorrect. Now we are just a few steps away from the final answer. Remember that b divided by k is the published margin of victory, MOV. For the close election case that we're interested in, the natural log of 1 minus MOV is approximately equal to minus MOV. The natural log of 1/10 is equal to the natural log of 10, which is almost exactly equal to minus 2.3. So the number of Jacob voters who need to check is approximately 2.3 divided by MOV. In an election with 100,000 actual votes for each candidate and a 1% published margin of victory, that's 230 voters, or 0.23% of Jacob voters. For reference, every election to the U.S. House of Representatives gets around 200,000 total votes. In this scenario, it doesn't matter how many Edward voters check. But wait, what if the election authority is really malicious and profiles the Jacob voters to target the ones who are least likely to check? If the average targeted voter is, for example, 3 times less likely to check than the average Jacob voter, then the overall number of Jacob voters who check needs to be 3 times greater, or 0.69% in this example. Thank you to the viewer who asked this question. To his credit, he also provided his own analysis, which is basically the same as mine. Thank you for watching and have yourself a great day.